And now it's finally time for Max. So Max is here from the Ukraine, which is, given the circumstances, also very special. I met him at CocoaHeads Ukraine. He's a really awesome guy, and he's going to talk about reverse engineering. Give it up for Max.
Morning, everyone. Oh, yeah, it's working. Okay, as Chris said, my name is Max Bazaliy. I'm an iOS developer from Kyiv, Ukraine. And today I share my thoughts about practical reverse engineering. We will check the possible tools and possible solution to prevent the reverse engineering. A few words about me. In Ukraine, I started CocoaHeads Ukraine and iOS developers community. Right now, I'm working on iSecurity Kit. It's a security framework for developers to prevent reverse engineering and data leakage. And my thoughts about reverse engineering and iOS development could be found on Twitter or GitHub. So, very popular question that I hear, why we need reverse engineering. First of all, it is a security audit. It is the possibility to check our application, to check weak spots in our application just before submitting it. Or this analysis of our competitors. We can analyze the solution of our competitors and check the good ways and know how to improve ours. I have a few examples in my lab. And of course, solution advantages. You can reverse engineer a closed protocol or a format and add a support of this format to your application. A great example is AirPlay protocol that is closed by Apple, but many software on macOS is supported. And of course, it's fun. It's fun to check and understand how the things are working under the hood. Let's start from analysis. Analysis could be done on system level and on a code level. System level includes traffic sniffing, it's tools like Charles proxy, model call tracing, tools like dtrace, input-output activity of file monitors, loggers, etc. The most interesting one is code level. It contains disassembling, decompiling, debugging, and reversing of internal application resources. We will start from this. First of all, we need to check the internals of the application. Just double-click, show package contents, and we see a lot of files. First of all, binary files, image files, interface files per list, and core data models. I will go through them quickly, how to reverse them. Image files. What's the problem with image files? Sometimes after the compilation, image files are compressed, and usually viewer utils are not able to show them. It could be uncompressed with png-crash utility or just automated with app-crash Ruby script. It will find all the compressed resources across your application and decompress them. Another great tool is Artwork Extractor. It works with applications and with frameworks, including the Apple frameworks. So with this tool, you can grab all the emoji icons, everything from UIKit. But do not store it into App Store. Apple guys will be sad. Next one, interface files. Usually it contains NIPs, which are compiled XIPs, and storyboards. Storyboards, just folders with XIPs inside. Interface builder are not able to show them until we apply NIP patch or NIP decompiler to it. And core data. Core data contain MOM files, which can be reconstructed to initial XC data models using a MOM decompiler utility. And binary left. A quick overview of tools that we'll talk about today. OTool, a disassembler tool from Apple guys that are from Xcode tools package. Class dump, a util to reconstruct initial class interfaces. Match your viewer, a tool to view and change, match your headers, match your binaries. I will show it later. Hopper, a disassembler and decompiler utility. A SciCrypt. SciCrypt is a tool that allows developer manipulate and change the application behavior just in runtime. And reveal for viewing view hierarchies just in runtime. A few words about macho binary. As we know, all the executable files on iOS and macOS are the macho. So it starts from a header that contain 4 magic bytes. I will talk about them. And load commands. Load commands, in other words, it describes how our data and code will be mapped into memory. So it contains code sign-in commands, dynamic libraries, constants, and all the code section. And the magic bytes. So for 32-bit, or ARM6, ARM7, the magic 4 first bytes of the binary will be feed phase. For 64-bit or ARM64, it will be feed fast. For universal binaries like FAT files, which contain more than 1 architecture slices, it will be a cache baby. Yeah. So here's an example of macho view utility. We can see the FAT file with 3 architecture slices, ARM7, ARM7S, and ARM8. The point of interest in is text section, which contain code and read-only data, and Objective-C sections, which contain data is used by runtime. So it contains all the class names, all the method names, all the IVARs name, all the protocol names. In other words, everything that could be used to reconstruct initial class structure. It is a very good advantage of Objective-C because other language like C or C++ doesn't contain this internal information. So what we can do, we can use the class dump Z utility to reconstruct the class information. It will look like this. So everything, methods, properties, IVARs, everything is reconstructed. But it could be a problem with decrypting application loaded from an app store. They are encrypted, the code section are encrypted, and analyzing tools will not work with them. The good news are that any encrypted code will be decrypted before execution. So our goal is to find it and grab when it's decrypted into memory. Step number 1. Use a tool for analyze our binary, filter LC encryption load command. It will show the position and the size of encrypted size inside your binary. For each architecture, it will be the different numbers. The next step requires jailbreaking of your device. Right now, for iOS 7, only one possible solution is evasion, could be found on evasion.com. Another steps could be complex, but I will run through them really quick. We need to calculate the address and size of encrypted code into memory. We need to attach a debugger and dump this decrypted code section. But it could be a problem with ISLR. ISLR is system protection mechanism to avoid exploits. In other words, it arrange the code section, the heap, the stack into randomly places inside memory. So we can bypass it by finding the code section by signature or filling all the free memory with some junk. So as example, our code should be mapped in address 1000, but it will be mapped, for example, in address 5000. Okay, we'll defeat it, dump the code section from a memory, insert it inside binary, and patch a header. As we see, it required a lot of steps, and it's kind of difficult task. Of course, there are tools that could help to automate all these things. For example, Resticrack, Clutch, or dump decrypted tools. They will analyze the binary, attach debugger, bypass SLR, dump a binary, patch a crypt ID. So as a result, we get fully decrypted binary that are ready for analysis. A few words about analyzing tools. Right now, there are two good instruments for this, Hopper or EDA Pro. Both support disassembling, decompiling, debugging, but EDA supports a lot of architecture and processors, and it's really, really expensive for one person, about $5,000. So my choice was a Hopper. When we open our application in Hopper, we see a lot of calls. As we remember, all the method calls will be invoked into opc msgsend C function. It looks like this. So the first parameter is a receiver, the other one is a selector. 80% of all the calls will be invoked to opc msgsend. It is really helpful for reverse engineering. So let's open one of the methods inside the disassembling tool. It is an example of Hopper disassembler. On the right, we can see the decrypted method names on the left, decrypted method names on the right, the disassembling. The disassembling include internal calls of internal RC methods like RC retain, RC after release. The next great feature of a Hopper disassembler is control flow graph. It shows all the possible branches of your program, all if-else, switch cases, whiles. All of this will be represented into this graph. So it's really useful for static code analysis. The last thing in Hopper is the compilation feature. It converts the assembling code into readable pseudocode, usually it's C. In this result, it traces all the opc msgsend methods and converts them in readable names like you can see your application, shared application, or URL with string. So it's really useful in Hopper. Usually, it's no need to reverse all the application. We need to find the algorithm realization or find the additional functions enabler. So what are the good places to start? First of all, method names. Usually, developers are using code conventions, and if you're looking for a login method, there are big chances that it will be on a login with name, something like this. If there are no luck, try finding for strings. For example, string like password is incorrect. There are big chances that this string is used into password checking code. And of course, constants. If you know the cryptographic constants like MD5 or IS, you can say, oh, okay, this code is using a crypto. All the crypto analyzers, static crypto analyzers work like this. They're just looking for a constant. The next big thing is SciCrypt. SciCrypt is a hybrid of Objective-C and JavaScript. It allows us to manipulate application just in a runtime. It can dump headers, the same like we made with class dump Z, but in a runtime. Modify ivars, instantiate objects, invoke methods, or swizzling methods. Who know about swizzling? Who tried it in your code? Oh, okay. So the good news are that we can do swizzling just in runtime. So in this example, I changed the implementation of each jailbroken method in jailbreak detection view controller just to my function that return always no. So that's all. No need to exchange implementations and other things. Or we can invoke the methods like UI application, invoke key window, find the subuse, next responder, top view controller, and we got a navigation controller. So with the SciCrypt, you can explore everything just in runtime. Really useful one. Next thing is a reveal. I think that you guys using it, reveal or Spark Inspector. It's allowed to inspect view hierarchies in a runtime and visualize it with a 2D or 3D. The good news is that it could be injected or dynamically loaded for every iOS application. So there is an example for a Foursquare app. On the left, we see a view hierarchy. On the right, we see a 3D visualization. Try it with Apple tools. They're really interesting view hierarchies. Of course, there are special tools for reverse engineering and penetration testing, like IDB Analyzer, Snoopit, Introspy, IRED. But none of them are working properly with new ARM64 devices, and right now I will not cover them in this talk. So, as we see, there are a lot of ways to reverse engineer application to manipulate it or explore it. The good news are that we can implement the best secure encoding practices or security tricks to protect our application. A few words about best practices. First of all, always compile your binary with a pi flag, which enables ISLR. Do not store any credentials in a pi list. Disable NSLog in a release. Yeah, it sounds funny, but I saw a lot of applications that forgot to do this, and all the information is just in a log. Use NS file protection attribute for all the user-sensitive data like photos, text files. Store the sensitive data into a keychain. Be careful with view snapshots. As we remember, application when entering background, system is taking a snapshot of the current application screen. It could contain passwords or it could contain credit card information. Make sure you erase it before making a snapshot. Be careful with the caching policy, because especially if the API you sending is sending a passwords or logins. I saw a few applications that forgot to disable a caching for authorization methods, and all the passwords and logins could be retrieved just through a database. It is accessible without a jailbreak. Be careful with URL schemes. From iOS 5, it is a possibility to validate the input application, and read the secure coding guide from Apple. They released it a few months ago. It's really interesting. The next steps. As we see, all the Objective-C methods are storing the runtime information into a binary, so our solution will be not use Objective-C in the critical code section. Use C functions instead. Implement integrity checks, SSLpn, and code and strings obfuscation. We will talk about them very soon. So let's check the possible code examples, how to implement it. SSLpn. Who uses SSLpn in your applications? Okay. So SSLpn is a technique for validating the remote certificate from a server with a certificate on the client side. If the certificate are not the same, just broke a connection. It could be realized, it could be implemented like checking of public key or the whole certificate. So there is an example for an URL session. We should implement URL session did receive challenge with completion handler and load our SSL certificate from a disk and compare it with the certificate gathered from a remote server. If are the same, okay. If not the same, it is a big chance that we are being hacked. For IF networking, there is a more elegant solution. All you need to create IF security policy object, set the arrays of pin certificates, and set the SSLpn in mode. After that, just set security policy on operation manager, and all will be working just out of the box. Method obfuscation. As I say, do not use Objective-C methods, use C functions instead. Don't forget to strip symbols from the debug symbols during compilation inside your application. Use a define trick to hide real function names. I will show it a little bit later. And for C function, use inline and always inline compiler attribute. So here is a define trick. As we see, we define the readable function name with something unreadable. In our code, we can invoke function with a readable name. In this example, is jailbroken. But after compilation, all of this will be just blah, 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 like GB, so it will not help cracker to understand what this code does. But is jailbroken will help. Okay, obfuscation of strings. The simplest string obfuscation is just XOR, or substitution of symbols. So symbol A became a symbol B became a symbol C. The good thing that string length will be the same, And it is a really cheap operation to decode and encode it. Use encoding and decoding tables for it. Of course, you can implement something more complex like iOS or DES encryption. One advice, do not store the same key for all your applications. The cracker will find it just once and crack or decrypt all your strings inside all the applications. Here is an example of decoding a string using a decoding table. So we store a string into decrypted format inside the binary and use define with some readable name to understand which is the string, and decode it just before using into memory. There is an open source project, REncryptor, that can help with the easy API protect your images, sound files, and other stuff. So try it. Anti-debugging tricks. As we know, most reverse engineering tools are using a debugger to dump and trace our code into memory. So if you can detect the debugger, we can protect our application better. So for example, we can, if you detach our application from being debugged, we can change the application behavior, like returning a nil object instead of real ones in the constructor, or change the whole values of the application. So let's check it. Don't worry about the code. I will upload slides just after I talk, so you can check it more detail. This code is checking for current process flags, and if the ptrace flag is enabled, it means that we are being debugged, we can do something bad. This code showed the old trick with a ptrace function with a ptDNA attached string. Execution of this code will crash any debugger Xcode as well. But this trick is well known by skilled crackers, and most of the automating cracking utilities are bypassing it on the fly. So I found a way how to use this trick by calling ptrace in indirect way using a syscall. So as you see, 5 magic numbers. So the first number is a constant for a ptrace. The second one is constant for ptDNA attach. And execution of this code will crash any debugger, Xcode. The good thing that it's not detected by cracking tools, and it could not be cached by putting a breakpoint on the ptrace function. So use it. This code shows how to change the object implementation in a case that we are being debugged. So if we are being debugged, we return nil instead of real object. If it's okay, we return shared purchase manager. We can implement integrity checks. We can check a few characteristics of our binary. If it's been changed, do something bad. For example, we can check is our binary being encrypted. As we remember, all the binaries to analyze need to be decrypted, and all the binaries from App Store are encrypted. So if it is decrypted, we are being correct. Is our code section being modified, or is it being patched? Is internal App Store information like SC-info or iTunes metadata exist in the application? Usually, cracking tools strip this data. And is our application contain dynamic libraries that are usually used by cracking tools? So that will be a lot of code. Please, attention. This code is checking for LC encryption info section, checking for a crypt ID flag. If it's not 0, so if it's 0, we are being cracked and the binary is decrypted. So we can put it, we are correct. This code is calculating the checksum of the code section and compare it with the checksum that we are stored inside our binary. If it's not equal, we are being patched. This one is checking for ST-info folder. This folder is always exist in the application downloaded from an app store, and this folder should always contain 2 files. Usually, automatic cracking tools strip this information. If it's not exist, we have been cracked. The same for iTunes metadata plist. iTunes metadata plist is a file that contains information about Apple ID account who is downloading this app, like email, like internal information about ratings. Usually this information is also stripped by cracking tools. If it's not exist, we are being cracked. The next two slides will show how to defeat overdrive. Overdrive is a special cracking utility, a library that is loaded before your main code and bypassing almost all cracking protections. So we just hook functions and change their behavior. How we can defeat it? First of all, check our binary main bundle for dialib files. As we know, Apple doesn't allow us to release application with dialib files inside, so if it is, we have been cracked. This trick is trying to find the cracking tool classes in a runtime, if they exist, changing the implementation of alloc with on method to a nil implementation. So in other words, the cracking tools will be not able to allocate its classes in a runtime. So use it, it is still working with the cracking tools. So integrity checks, debugging checks, everything. We detect that we have been cracked, the integrity was changed. So what we can do? First of all, terminate our application. As for me, it's not a good way. Better to run application in a demo mode. For example, is it a game to allow user play only a first level of the game, or change the whole application behavior. Usually, PC copy protection systems using this way. For example, it integrate all the game triggers on checking the copy protection. For good example is Go63 game that is checking for binary integrity. If it's broken, multiply all the prices in a store by 1 million, or make all the enemies immortal. So game is still playable, but it's really hard. The bad news for cracker is that these tricks are really hard to find. The cracker should solve all the game to understand how the things should work in a normal way, then compare it with the cracked one and find the protection tricks. The last topic is jailbreaking. As we understand that most of the cracking tools are running into a jailbreaking environment, and jailbreaking is reduced the application security, the system security. So how we can detect it? There are a few ways. Check for a file that is stored in a suspicious path. Check for URL handlers. Check for accessing some system files. Checking for a root, or checking for a current running processes. A quick overview of these tricks. This code is pretty simple. It tried to write a text file inside a private folder. If it's not return an error, we build jailbreaking. The next one is more interesting. It executes the fork function. Usually all the applications are running inside the sandbox, and system doesn't allow to create the child processes. But after jailbreaking, applications are sandbox free, and the fork function will create child process. So we just check for return value of a fork. If it's 0, everything is okay. If it's not 0, we are inside jailbreaking environment. The next one is simple check, can any application handle CDR real scheme? Usually the CD app can handle it. If it is, we are building jailbreaking. Next code is just checking for a path, suspicious path, for a CDR, for SSH client on our device. If these files on this path exist, we are building jailbroken. And the last one is checking for current running processes. If it contains mobile CDR, we are building jailbroken. All of this code doesn't allow any jailbreak, so you can use it in your applications. A good one is Project IMS. It is an open source solution for iOS applications. It have a great feature like encrypted core data, which supports SQL cryptor with the core data. It have implementation of security checks that I'm talking about. It has a good feature like a passcode check. It tells you from a code check is device is being protected by a passcode, especially if you're using bank software. It is a good feature. And memory security for securely wiping of a memory. You can check it on a GitHub. The next big thing is a LLVM obfuscator. It tells obfuscate binary code from static analysis. A few features like instruction substitution. It will add a lot of junk instructions to our code. So the execution speed will be much slower, but it makes the static analysis really impossible thing. The next two things, control flow flattery and bogus control flow, adding a lot of fake branches to our code. So analyzing of control flow graph will be impossible. Our code will still run in the one way, but a lot of fake branches make cracker life really, really sad. As for me, the LLVM obfuscator is really big thing and really big win with obfuscating Objective-C code, and I hope in the future we'll see more code protection tools for iOS apps. The last thing I want to say is that cracking time is equivalent to a protection time. If you spend just 5 minutes to protect your app, the skilled cracker will spend just 5 minutes to crack it. So make a balance between security implementation and the time. That's all from me. So